Today in Applied Calculus, we're going to get to the other half of calculus. We have been doing derivatives, and we are now going to learn about something called antiderivatives, which, as anti would imply, is going to be actually undoing derivatives. So we're going to be working backwards. So previously, we had been given an original function and asked what the derivative is. We're going to turn things around a little bit. It's kind of like in Jeopardy, where the host gives you the answer and you have to come up with the question, right? So what used to be our answers are now going to be the problems, and what used to be the original, statement is going to be the answer that we're trying to find. So we are turning things around. Now what a question might look like is, suppose you know the answer to a derivative, right? I've got that prime notation, is 7. Which function was the original function? So what function has a derivative that is equal to 7? So take a minute and think about it. You've done enough of these that you can think backwards. Oh, if my original function was 7x, the derivative of 7x is 7, and so I found the answer. So in the beginning, we can just kind of think backwards like that. So then the question is that the only answer? We're used to a world where we did just get a single answer every time, and that's not going to be the case anymore. So is there another function whose derivative is 7? Well, if you remember that the derivative of any constant is 0, then there are actually infinitely many answers we could have come up with. Crazy constants. 7x plus 325. Its derivative would be 7 plus 0, so 7. 7x minus 1,000, 7 plus 0, or minus 0, so 7. Or even some constant like pi. So it turns out that if we had chosen any constant, this would have worked. So all the various answers we could think of, and you might have thought of some others, had that same 7x piece, but they had some constant that we could add to them if we wanted to. So in general, what we're going to do is write our answer as f of x equals 7x plus c, where c is any constant. And it could be positive or negative, so that's why this part doesn't matter. So what we just did was the reverse of differentiating, which means to find a derivative, and we anti-differentiated. And what we found then is an antiderivative, so the opposite of a derivative. So you could be asked to anti-differentiate x squared. What then you're asking yourself is, what function has a derivative that is equal to x squared? So what did we take the derivative of to get x squared? And so we can think backwards a little bit. Now we see that it would involve the power rule, and we know when we take the derivative of a power function, we bring down the power and subtract 1 from the power. So we know that our power should be 1 more than this, because if I took a derivative and now it's a 2, then it must have been a 3 before. So your initial guess might be that the answer is x cubed, because you know then with the power rule, you would have had your power go down 1 when you took the derivative. But then if we actually go check that, if we thought the answer was x cubed, what would the derivative be? It would be 3x squared. And we didn't have 3x squared, we just had x squared. So we're going to need to fix that. So we need to take this proposed answer and divide it by 3 to get rid of this 3 that we don't have. So we're going to revise our guess of x cubed, and it turns out that we actually need it to be x cubed over 3 based on what we noticed. And then don't forget that we said any constant added to it would also be okay. So then we want to check this answer. And I can even add my plus c down here. So now if I take the derivative, remember, and we need to get good at this, be comfortable doing this, x cubed over 3 is the same thing as 1/3 times x cubed. And thinking of it that way lets you pull out the constant, since we're allowed to, and just focus on the part that actually has the x involved. So if we're putting that c back in there, I'll add another plus the derivative of c. And and you'll see it's still okay. All right, so I've got 1/3 times the derivative of x cubed. The derivative of x cubed is 3x squared. The 1/3 and the 3 will cancel each other, and we really will get that x squared that we talked about. And again, even if we checked our full answer with the plus c, the derivative of that term would be 0. So even if you thought of it as x squared plus 0, which is x squared, you get what you started with. So we can do a little bit of this backwards thinking where, because we're so good at derivatives now, we've done enough and seen enough that we can kind of think, well, where did that come from? So I know that the power had to be 1 more, but that didn't quite work out, so how can I fix it? Oh, it had a 3 I didn't want, let me divide it off. But we want to actually establish some rules so that we're not going through that train of thought every time. So a few more definitions. One thing to note about that last example is the directions in and of itself. The word is so long. Anti-differentiate is so long, and Microsoft Word doesn't even think it's a word, but it is. So we have a symbol for this, and so that it's a little bit quicker. Just like instead of me always saying, please find the derivative of some function, we had d dx, and that was a quick way to do it. So similar. So the process of anti-differentiating or finding an antiderivative can also be known as integration or integrating. The notation for it is this symbol. So it's not an S, okay? It is an integral sign. And you have an integral sign, some function that you are anti-differentiating, and then this dx is notation, and we're going to define each piece. So in general, what we're going to get is the function that if you take its derivative, you would get this inside function. And don't forget about the plus c, where we could add any constant and it would still work. So we would have, this is called an indefinite integral. And of the function f of x with respect to x is what the dx tells us. And we get f of x plus c. So remember the constant c, it's called the constant of integration. And it can have any value. And that's why this answer is indefinite. So these are indefinite integrals. We'll eventually get to definite integrals. This is called the integral signed. And the function inside is called the integrand, okay? So whatever is inside the integral sign is called the integrand. We should be able to check our answer when we get an answer to this problem by taking the derivative, antiderivative, derivative, right? They should undo each other. And we should get the integrand if we've done it right. So while this might be new and unfamiliar, the nice thing is that we always have a way to check our answer. Okay, so then the dx, right now, it really is just notation that tells us what we are integrating with respect to. So something to really be careful about is that the integral sign and the dx go together as a package deal. So those together say, please find the antiderivative of f of x. And we're going to visit that a lot more, especially in the next section. So now with that notation, instead of saying, please anti-differentiate x to the 8th, you can just be asked this. The integral sign, x to the 8th dx means please find that antiderivative of x to the 8th with respect to x. So one last time, let's kind of think through. We know with the power rule, our power would have gone down by 1. So if we thought the answer was x to the 9th, well, think about what the derivative would be. The derivative of x to the 9th would be 9x to the 8th. But I don't have 9x to the 8th. I only have x to the 8th. So I need to divide off the 9 I would have gotten. And then don't forget the plus c. So on every single one of these, you can pause and check by taking the derivative and seeing if you get what's inside. And here you will. Here's one more. So last time we're going to kind of think through it. Well, e is a really special function, right? It was the coolest one ever. So if we're trying to find what function has a derivative of 5e to the x. So remember what's special about that. The thing I want you to notice is that this is a different rule and a different line of thinking than the previous couple problems. Because the previous problems were power rules where x was your base, your variable was your base, and you had a number in the exponent. Here we have a number base. Remember, e has a value. It's 2.71 and it goes on forever. And the variable is up here. And they have different derivative rules, so it seems to make sense that they would have different antiderivative rules. Okay? So don't drink and derive. You do not do what we've been doing where you make the power more and then divide by the power, because it's a different kind of function, but it's easier than that. Who has a derivative that is 5e to the x? Well, e to the x is its own derivative, and 5 is a constant that stays. So 5e to the x has a derivative that is 5e to the x. So the answer is 5e to the x plus any constant. And remember, we could check it, and I didn't add the plus c in there again, but of course its derivative would be 0. The derivative of 5e to the x is 5e to the x. And so we have our answer. So don't make that one harder than it is, and don't try to apply the other rule. So now we're going to summarize the rules that we do have. So these are going to be the rules that you are responsible for. We're going to have 3 antiderivative rules. And you'll see that they're related to the basic derivative rules we learned at first, okay? So if you have x to a power, what we saw by thinking through it is that we ended up adding 1 to the power and dividing by the new power. And then we always have our plus c. So if you want to think about why that is, we are undoing the operation. Okay, so I want to help you understand why this rule is what it is based on what you already know about derivatives. So an antiderivative undoes a derivative. So if you think about undoing something, silly example, but it works. If you put your socks and shoes on and you want to undo that, well, when you put your socks and shoes on, you first put on your socks and then put on your shoes. If you want to undo that, you don't start with the socks because that'd be awkward, right? So yes, we need to undo the on with an off, but I also have to undo the order of my operations because I can't get the socks off before the shoes off. So I put on my socks, I put on my shoes, then I take off my shoes, I start at the end and undo it, and then take off my socks. So we need to do that if we're going to undo this derivative rule as well. So for the derivative of a power rule, of a power function, we bring down that old power, we multiply in front by that old power, and then subtract 1 from the power. So we do need to undo these operations, but we also have to undo the order. So we're going to start here with the subtracting 1 from the exponent. We're going to undo that first, like taking off our shoes first. And so instead of subtracting, we're going to add. So we're going to add 1 to the exponent first, then we'll backtrack and undo the other thing, the socks, right? And so instead of multiplying, we will divide. So it was multiply by the old power and subtract 1 from that power. Now we're going to start here and add 1 to the power first, then divide by that new power. So I hope that helps you remember it. Now notice that this says that we do not use this when n equals -1. So be very careful of this. Why don't we use it when n equals -1? Well, because then it has its own rule, right? If the power is -1, that is 1 over x. And we know a function who has a derivative equal to 1 over x, and that function is ln of x. Now, something that your book and pretty much every other book does is puts absolute value there on the ln so that you're not worried about taking the ln of a negative number, right? Because we know that that isn't allowed, and they're just kind of magically saying it's going to be okay. All right, so we've got ln of the absolute value of x plus c. So that is a separate rule. Now, because of that, when we get to a problem, I will show you, I do not recommend rewriting anything that has just x to a 1 power in the bottom, because if you rewrite it as x to the -1, you're going to be tempted to apply this rule. But anything else, like if you had 1 over x squared, I would rewrite it as x to the -2 so that you can appropriately use that power rule. And then in the middle here, we have the coolest derivative ever, right? So coolest antiderivative ever. If the derivative of e to the x is e to the x, then the antiderivative of e to the x is e to the x. So I really did do it, but it's its own derivative, and all of them have the plus c. Now, we don't end up going too much into it in this class, but a integral, an antiderivative, is actually formally defined by a limit, and it all goes back to those limit laws. So we did need to at least acknowledge them because they are the crux of everything else. So since this is actually formally defined with the limit, just like we have the limit definition of the derivative, there is a limit definition of an antiderivative. And so all those limit laws apply here for integral, since an integral is a limit. So if you have a constant inside, you can pull that constant out and just focus on the function part, the x part. If you have a sum or difference of functions that you're trying to find the antiderivative of, the integral of, you can break it up into 2 separate ones. Now each one will have its own little dx, because those are a package deal that say, please find the antiderivative. So we're going to work on applying those, and just like with derivatives and even limits, I guess, we might show more steps in the beginning and then kind of wean ourselves off of that. So it's totally up to you how many steps you show. I will show a lot in the beginning and then kind of jump more to what I think you'll probably do by the time of the test. So first of all, I have multiple terms. So one of our rules said I can break it up to be two separate integrals of two nice little functions. We had another rule that said any constant that's in there can be brought out so that you can focus just on the x part. So that's what I've done here. Then we're ready to actually do these antiderivatives. So the 3 is a constant that stays. There is a hidden 1 power there, and our reverse power rule says that we add 1 to the power and divide by the new power. Now, the dx is gone, and so is the integral sign because I did what it asked, right? Just like when we took a derivative, the ddx sign disappeared. These disappear because I did what they said. I took an antiderivative. And then here, the 5 stays, and then I add 1 to the power and divide by the new power to get x to the 4th over 4, and then I always get my plus c. Now, because this was written as 2 separate integrals, you might think I should have written a plus c with each, and you would be right. What you sometimes will see the very first time is write plus c1 and plus c2, but remember these c1s and c2s are arbitrary constants. They could be anything. So one big constant here at the end eats all those up and takes care of everything. If I have an arbitrary constant plus another arbitrary constant, I get an arbitrary constant, and it covers everything. So I do need to make sure this shows up immediately once I have evaluated any of the integrals, but 1 can suffice for all of our separate terms. Okay, and then you can write it just like that, or this was just kind of cleaning it up a little bit. And that's our answer. Remember that for every single one of these, you can take the derivative of this function, and you should get the integrand. So feel free to pause it and check for yourself that that really does give you, and so it really does undo a derivative. All right, here's another one with multiple terms. So again, I can go term by term with anti-differentiation, just like I was able to with differentiation. I can also bring any constants out in front, and notice that I went ahead and rewrote this as well, because just like with the regular power rule, the reverse power rule must have x to a power where that x lives in the top. So if you had something in a denominator, you would need to write it with a negative exponent. If you have something in a root, you need to write it with a fractional exponent. So I rewrote it so that I can apply that reverse power rule. Now I'm ready to apply the rules. Now be careful because I have 2 different rules here. This is an exponential e to the x, and who has a derivative that is e to the x? E to the x. So that's the answer to that, whereas this other one is a reverse power rule problem. Add 1 to the power and divide by the new power. Don't let the simple math be what messes you up. If you need to go to the side and write 1/2 plus 1, oh yeah, that's 1/2 plus 2/2 to see that's 3/2, do it. Okay, don't let that be the reason you miss something. So I'm going to add 1 to the power and divide by that new power. You may not show all these steps eventually, but I'll get 3/2. Now I could write it as dividing by 3/2, but remember that division by a fraction is the same thing as multiplying by the reciprocal. So me and many of my students end up just saying, if that's a fractional exponent, I'm going to just immediately go ahead and write times the reciprocal instead of divided by, because I've got a complex fraction and it's just not as nice to look at. So you can do that in 2 steps or 1, doesn't matter to me, but do remember that division by a fraction is multiplication by the reciprocal, and that's how I ended up with 2/3 there. And then the last thing is, if you are asked to have no negative or rational exponents, just like you did with derivatives, then you need to be able to rewrite it. So remember, it's power over root, so it would be a cubed and a square root. And so this would be my final answer. You can see that the second I applied those rules that were on the last page, the integral sign, and the dx's were gone, and instead was a plus c. So that needed to be right there, not just shoved on at the very end. Okay, and here's one more, and this one is what I was warning you about, a combination of things that look similar but behave differently. And so if I were to rewrite this, I would not, now I could separate the 2 out if I wanted, but I would not write this as x to the -1, because if you do, it's going to tempt you to apply the reverse power rule when it doesn't apply there. Instead, I would leave that there to remind yourself it's its own rule, right? Because who has a derivative that's 1 over x? ln does. But with the x to the fourth that was in the denominator, it is going to be a power rule problem, and it needs to be rewritten with x up top before I can apply that reverse power rule. I cannot dive down into the bottom and do that reverse power rule, just like I couldn't for derivatives. Okay, so then if you want to still be breaking it up term by term, each one gets its own sign and dx. You can see here I did pull out the 2 so that I am just focusing on what I know will have an answer of ln of x. And then I will go term by term and apply the antiderivative rules. So remember, our opening example was who has a derivative that is 7, and it was 7x, right? So here, who has a derivative that's 1, and it's 1x. It is actually the reverse power rule. It's just kind of a weird one to look at because right now it's x to the 0, but it does actually fit. So this is x. The 2 is a constant that stays, and ln of x is the antiderivative of 1 over x. And then here I add 1 to my power carefully, right? Negative 4 plus 1 is negative 3, and divide by that new power, and then I cannot forget my plus c. So cleaning things up and not writing negative and rational exponents, negative here, I have x minus 2 ln of x minus, so the 3 was already in the bottom and it belongs there. Now I can put the minus out in front instead of down there. That's okay, or not, whichever one you want to do, but this has to move. So the negative 3 exponent goes on the x, which means the x belongs on the other side of the fraction bar, and once it's there, it's happy, it's positive, and so now it has a positive exponent. So that would be the cleaned up version of the answer. Okay, so one more of these where we've got, now these are actually all power rule problems, but we do have some rewriting to do. So make sure that you do rewriting first, okay, and so if it didn't need to be rewritten, then I literally rewrote it, like copied it. And then if I had power issues, then I rewrote them. And so this one ends up with lots of 3's, right? So I'm going to add 1 to the power, divide by the new power. Now here, the 3/2 stays. When I add 1 to 1/2, I get 3/2, and I divide by 3/2, or think of it as multiplying by the reciprocal. In either case, it will cancel. Plus, here I have a negative 4/3. Be careful. Like I said, go to the side if you need to. I'm adding 1 to that, but I have to have a common denominator, so hopefully that helps you see why it's negative 1/3, okay? And then I'm dividing by that new power, negative 1/3, and I have my plus c, so then I'm just cleaning things up. So I have x cubed over 3. The 3/2 happen to cancel. That won't happen every time. It was just because of the constant that was there. And x to the 3/2, it's power over root, so it's a square root and a cubed power, third power. And then this negative exponent means that this actually belonged in the denominator and under a cubed root because it's 1/3. And then we have our plus c. Now dividing by negative 1/3 is the same thing as multiplying by negative 3. So you can see there's my negative, and that's why the 3 is up top. And then the x had moved down because it had a negative exponent. So if the directions say rewrite without negative or rational exponents, that would be your final answer. So the last thing that we'll do in this section is sometimes we can actually identify that plus c. So when we find these antiderivatives, we're actually finding a whole family of functions. That's what that plus c is doing. So for instance, if I integrate x squared, I get x cubed over 3 plus c. And if I were to actually plot those, there would be even more. There would be infinitely many. So they're all going to have the same shape to them, that x cubed over 3 shape. But the plus c basically is like your intercept of sorts, that it's going to put how high or low it is. If it's plus 7, it's up here. If it's minus 3, it's down here, right? So this is just sum of the infinitely many. They're all going to have the same shape because of slope and that idea that's associated with derivative. But how do I know which one I mean? So what we're going to be doing is given an initial condition, and you've probably heard of that in science class at some point, an initial condition, a value I know about the function to say, I mean that one, right? So instead of getting a whole family of functions, I can identify the particular one I'm talking about based on one fact I know about the function. Okay, so we can find out exactly which antiderivative we are talking about if we are given an initial condition. So this is an example of what a problem would look like. I need to find the function who has a derivative of x squared, but then instead of just getting, we got a preview of this, x cubed over 3 plus c, I can actually find out what that plus c is and find the exact function I mean. So why is this worded the way it is, right? Find f such that f prime equals, because we are doing an antiderivative, right? If I do an antiderivative of a derivative, they undo each other and I get back to the original function, right? So that's what we've been doing. So my function will be what I get when I find the antiderivative of x squared, the given derivative function, and I will add 1 to the power and divide by the new power, applying that reverse power rule, and I will get a plus c. But they gave me a fact that is going to allow me to solve for c. So that's going to be the only new piece here. We're going to use the given fact, f of negative 1 equals 2, to solve for c. Be careful. This is actually quite simple, but I have students mix up the letters, so slow down. Remember, y equals f of x. So the f of, this is your x value, and what that equals is your y value. So this is the ordered pair negative 1, 2. So I'm going to plug these in to solve for c. So my output is 2, y equals f of x, right? Y is f of x. That's my 2. And I'm replacing all x's with negative 1. So I replace that with negative 1, and now the only unknown is my c, and I'm able to solve for it. So I have 2 equals negative 1/3 plus c. I need to add the 1/3. To do that, I would need a common denominator, so I rewrote 2 as 6/3, and I get 7/3. Now, what I see is oftentimes students are so excited they found c that they stop. And so the question did not say, please find c. The question said, find the function f. So all I need to do is go back and look at the function I had said was the answer, but now incorporate the c that I found because they had given me extra information. So the answer to this is that the function is the particular f of x equals x cubed over 3 plus 7/3, not just the whole family of functions where this could be any constant. So we'll look at one more of those. So I'll be given some derivative function and asked for an original function, and that makes sense because, again, we are anti-differentiating. We are undoing a derivative. And then they'll give me a piece of information that allows me to not just have a plus c, but to know exactly which one I'm talking about. So the function will be what I get when I anti-differentiate or integrate the given derivative function. I will apply my rules, whatever is appropriate. Here it's all reverse power rule. So the 6 is a constant that stays. I'm adding 1 to the power, dividing by the new power. The 4 is a constant that stays. Add 1 to the power, divide by the new power. And then who has a derivative that is 2, 2x. And then my plus c. Another really common mistake is students not writing plus c here, but then diving in with the 1 and the 9. If you dive in with the 1 and the 9 right now, you will not have an unknown. And I will write on your paper, what are you solving for? You have to have an unknown to have something to solve for. So if you get to a point where you don't have any unknowns, go back and realize you forgot to put the plus c. You've got to put that plus c. Also notice that I modeled more like what you might be doing as you go forward versus always writing the separate integral signs and showing a separate step to bring out the 6 and bring out the 4. So you show as much as you need to, but it's perfectly fine with me if you get to this point. Okay, so now I just clean this up. 6 divided by 3 is 2, 4 divided by 2 is 2. And I'm now going to use the given information to solve for c. So this is f of x, so x is 1, equals y, so y is 9. So I have the ordered pair 1, 9. So what I'm going to do is replace y, or f of x, with 9, and all my x's with 1, and solve for c. So I have 9 equals, and then I replace all x's with 1, and now I have just one unknown, right? If you got here and you didn't have the plus c, all you have is a false statement. 9 equals 2. That doesn't make any sense, right? So use that to catch your mistake and say, oh yeah, I was trying to find c. So plus c, these 2's cancel, but you still have a 2. So you have 9 equals 2 plus c. And then when you solve, c is 7. That is not the final answer. The answer is the function that makes both of these things happen. We initially had the one that made this part happen, but we did not incorporate the 1, 9 yet, and now we have. And so our final answer is f of x equals 2x cubed minus 2x squared plus 2x plus 7. And so as that example where we had a whole family of functions where we had infinitely many options based on the plus c, now we're saying, I mean that one. So we're just going to look at one final example that is the same thing as what we were just doing, but with a business application. So it says a company finds that the rate at which the quantity of a product that consumers demand changes with respect to price is given by the marginal demand function. So notice it says d prime, and it had the word marginal, which we know means derivative. And that makes sense because then they are asking us questions about the original demand function. And we know if we want to undo a derivative, then we will get to original function. We'll use an antiderivative to do that. So all of that actually makes sense that they're giving me a derivative function this time. The X is the price per unit in dollars, and that's going to be important because when you keep reading, find the demand function if it is known that, so some extra piece of information that you know that helps you solve for C. 1,003 units of the product are demanded by consumers when the price is $4. Students know that's supposed to be an ordered pair, but they get mixed up on what the order should be. So go back and it says X is the price per unit in dollars. So immediately the 4 is my X, and so the other thing must be my Y, the 1,003. Okay, so to get a demand function, that's what we were looking for, then I need to undo the marginal demand function, undo the derivative. So I'm just going to anti-differentiate or integrate the given function. Notice that I did rewrite it because I need to apply that reverse power rule, so I must rewrite it as x to the negative 2. And then I'm going to, the negative 4,000 is the constant that can stay. I'm going to add 1 to my power and divide by my new power. So negative 4,000 divided by negative 1 gives you 4,000, and x to the negative 1 means the x should be in the bottom. And we can't forget that we got our plus c. So this is the basic template for our demand function, but we have a specific piece of information that will help us find the particular one we're talking about by solving for c. So we talked about how I knew the order of my ordered pair, and I now have that x is 4, so I'm replacing x with 4, and that the output is 1,003, so I'm replacing my output with 1,003, and you can see it works out very nicely. So 4,000 divided by 4 is 1,000, subtract 1,000 from both sides, and you get that c is 3. It did not say, please tell me c. It said, find the demand function. So the demand function is that template function with the c plugged into it. So 4,000 over x plus 3. So that's it for this section. We just have our 3 new antiderivative rules, much like we had the 3 derivative rules, the basic ones when we first started. And then the last piece is just if you are given an extra piece of information, then rather than getting a whole family of functions, you can get a particular answer. So practice, practice, practice with those antiderivative rules, those indefinite integrals, because in the very next section, which is integration by substitution, we will already be expected to know those right off the bat and try to focus our attention on the more difficult new part. So make sure you really master those 3 rules and these initial value problems through the homework before you move on.